Ladies and gentlemen, we're going to talk today about the failure of fatigue. Fatigue and corrosion are the two worst failure phenomena that can happen to components and structures. Corrosion is mostly a chemical failure phenomena, like rust, and fatigue is mostly a mechanical failure phenomena. So when we talk about fatigue, what I'm going to do is have our lab manager, Mr. Jadong San, show you an experiment, and I'm going to give you synchronously a handout with a lecture about all what you need, and maybe I'll give you a PowerPoint presentation of the operation of the machine and of the formula that we use. But today I just want to give you an overview, which I'm going to start with before showing the experiment, before showing the notes, which I'm going to give you in real time, and before showing you the PowerPoint. So fatigue, what is the origin of fatigue? The origin is when you have a sinusoidal or cyclical or cyclic forces acting on a component. So for example, if I am to plot force or stress in KSI or in megapascal versus time, if I have a component which is exposed to tension and compression, then this is a cyclic or a sinusoidal stress. And we define the R ratio as compression divided by tension. And we like to put compression with a negative sign and the tension with a positive sign. So here, if I have minus sigma divided by sigma, and if sigma tension is equal to sigma compression, then the R is -1, and we call this phenomena, where R is equal to -1, as fully reversed. Many machines are exposed to a fully reversed stress. Also, you can have a different phenomena. You can have something which is like having tension 0, tension 0, tension 0, tension 0. There is still a cyclic behavior because you go from 0 to tension, to 0 to tension, 0 to tension. And as you have guessed correctly, that R here is a 0, because there is 0 compression divided by a value for tension. And also, you can have another behavior where you have all tensile load, but you have a maximum and a minimum, a maximum and a minimum. And also it happens in many components, and I'm going to ask you in your report to tell me what components are exposed to high and low stresses. And of course, you can have things which are not uniform. You can have like tension, a little bit of compression, tension with high compression. You can have what I want to say, a cyclic load, which is not uniform. But all these indicate that you have to have something cyclic or cyclical or sinusoidal. And the reason is, if I have a sample and I'm exposing it to a tensile load, and I'm exposing it to, let me get another color, and I'm exposing it to a compressive load, then what will happen is you have cracks in the material that are going to be formed, and these cracks are most of the time at the surface. Sometimes they are in the interior of the material. So what will happen is when you have the cracks, so we're going to have cracks initiating and then initiating and then propagating. So if I have a sample and I'm exposing it to tension, compression, the tension is going to make the crack bigger. The compression will make it smaller. But when you keep on doing this day after day, month after month, year after year, at the end, you're going to have a crack which will become big and it's going to break the material in two. So, what is the origin? The origin is sinusoidal load and cracks initiating and propagating. We're going to talk about the physics of the initiation and the propagation when we talk about the longer lecture that I'm going to do it synchronously with you. I'm going to send you the notes, PDF notes, and we're going to go over them in class. Now, what are the types of fatigue? We have basically three types of fatigue. One type, which we call high cyclic fatigue. And this is the type that we're going to study in our experiment. So, what is high cycle fatigue? High cycle fatigue is when the external sinusoidal, of course, sinusoidal stresses are less than the yield strength of the material. So you can imagine that the number of cycles to failure will be large because you are acting on it below the yield strength. And the number of cycles to failure are typically between 10 to the power 3 to 10 to the power 8. Millions upon millions of cycles. This is like if you have the railroad and you are having trains go over it, or the fluttering of the wings of an airplane, or the constant change in pressure inside the fuselage of an aircraft. One of the things that I'm going to ask you to include in your report is examples of high cycle fatigue. So this is one. The second one is called low cycle fatigue. In low cycle fatigue, you have the sigma external, tension compression, exceeds the yield strength. So in each cycle, you are deforming the material. I had a publication with a professor from UCLA about 20 years back, where we were given by a company something schematically looking like this, like a fork made out of titanium, and it was used by surgeons doing heart surgery, and they kept on bending that tool and then unbending it and then bending it in a different angle. They keep on bending it and unbending it to reach, different points in the heart. So typically, in this publication, after 25 times they keep on doing this, the sample breaks. In other applications, which again I'm going to ask you to do them in the report, you're going to find that there are lots of components which are exposed to low cycle fatigue. So what is low cycle fatigue? Is when you have low number of cycles to failure. Now, sometimes you can get 1,000 cycles, but still they are less than the number of cycles to failure in the high cycle fatigue. Now, the third one is a little bit of our work. I teach it in a graduate class. You see here in high cycle, it takes care of nucleation and growth of cracks. Same thing here, this phenomena takes care of nucleation and growth of cracks. The third phenomena is dealt with by a concept of fractional mechanics, which is fatigue crack propagation. So fatigue crack propagation is when I am dealing only with the growth of the cracks. And this is dealt with in a concept which we call fractional mechanics. And I'm not going to go through it here. When you become seniors or when you become graduates, we're going to talk about this part. But our lecture is going to be on high cycle fatigue. So we talked about the three types. The reason I'm showing you a type that we're not going to study is that while you're doing your literature search, if you came across fractional mechanics and fatigue crack propagation, you know that this is something we don't need to worry about at this level. Now I'm going to talk about the phenomena of high cycle fatigue, which is this guy. What do we do in the experiment? In the experiment, we're going to get samples. If we come here, we'll do it ourselves. If not, we're just going to see it with Mr. Jiadong Sun, our lab manager. You get samples looking like that. And these samples, as you see, they are tapered to have the thinnest area in the midsection. Why? Because we want them to break in the midsection. So you get this sample and you turn it, you rotate it. You put a load and you rotate it. And I'm going to talk about this more during the synchronous lecture. And I'm going to show you the machine. And Jiadong Sun will show you the actual experiment. But the idea is when you get the sample, you're going to expose it to a R is -1 or a continuous change in tension and compression. So at the beginning, you're going to have here, let me try to draw it. You're going to have here at the beginning compression and here tension. But as the sample goes 90 degrees in its rotation, because it will be rotating, and there will be a load here. As it is rotating, the compression will become 0 and the tension will become 0. You rotate another 90 degrees, the compression becomes tension, and the tension becomes compression, then 0, then the sample which started with compression again will go back to compression. So we are doing exactly here a R is -1 with sigma versus time. We have 0 compression, 0 tension, and so on. So how do we do the experiment? If we want to do a food experiment, and I have many students who are doing their master's theses on that work, and many undergraduates are helping them in the experiment, and are helping them in the thesis, and they're going to be co-authors of the publications. Typically what we do is, let's say that I would like to do a curve, which we're going to call now the SN curve. What is that SN curve? This SN curve means stress. I know sometimes I call it sigma, but because typically in the literature, they like to call it Sn. I'm going to keep it as S. And N is the number of cycles to failure. Number of cycles to failure. So I'm going to bring, like, say, example, have 15 samples. And I'm going to have, for example, here a 10 KSI or like 70 megapascals. And then here I have a 20, a 30, a 40, a 50, and a 60. So I'm going to put in my machine a sample, and I'm going to expose it to a 60 KSI, and I'm going to find that it will break here. So the number of cycles to failure is very small. Then I'm going to do a couple of other samples at the same stress so that I can get an average or a mean value. Then I do another sample at 50 KSI. So example 15, no, let's say like 30 samples, who cares? So I'm going to do stress at 60 KSI. I'm going to do another one at 50, let's say 3 samples apiece. I'm going to do one at 40, at 30, at 20, and 10. So when I do it at 50, I'm going to find that the number of cycles to failure is a little bit larger. When I do it at 40, even larger and larger. When I do it at 30, it's even more large. When I do it at 20, I'm going to find larger and larger. And if I do it at 10, maybe it will not break at all. Meaning that I'm going to find the sample is still not breaking, the motor is on, the machine is, the sample is still turning. Then after an hour, 4 hours, 5 hours, 6 hours, 7 hours, I said, you know what? I have a life. I'm not going to just sit down beside this stupid thing. I'm going to shut it down, take the sample off. Then you're going to present it this way. This means sample did not break. So, as you see here, I have a inverse proportionality between stress and number of cycles to failure. So if I have a material and I expose it to high stress, it will break very fast, and if I expose it to low stress, it will break at a longer time. Now, it's very important to understand that this type of work, there are lots of like variation in the samples. So if these values are mean values, and let's say that I pass a curve like this, if I take the actual experimental data, I'm going to find that there are lots of scattering. The reason is we don't know exact, I mean, if I can have the same stress, and I can have 3 samples, and in one sample the crack initiated at the surface, in another sample it initiated in the interior. So that's why I'm going to have a little variation. However, we are always going to have that the stress, when it's high, the sample breaks much faster than when the stress is low. So this is the high cycle fatigue, or the SN curve. Now the last part in this lecture is the differences between the behavior of different materials. Steel, for some reason, we don't know what it is, it has a beautiful property, and that property is it has what we call a knee or an elbow or an endurance limit or fatigue strength meaning that in steels, if I have S in KSI versus N in number of cycles to failure, you have in steel something looking like this. This is what we call a knee or an elbow or fatigue limit or endurance limit or fatigue strength. All these are different names for the same thing. What is the beauty about it? The beauty about it is that if you know the endurance limit or the fatigue strength, or where is the knee or where is the elbow, you can always expose the component, which is rotating, to a stress below that knee, and it will never break in fatigue. Now, usually, this happens at about 10 to the power 6 in like a million cycles in steels. Aluminums, on the other hand, titaniums, all other materials, they don't have this. They just keep on decreasing, whatever stress you give them. Now, it is good in engineering that we know about the endurance limit, because in steels, for example, we think that sigma endurance, which is all of the above, is half of the ultimate strength of, or the tensile strength of steels. This helps us in design against fatigue. If I know what is the ultimate strength of steel, I will know that my endurance limit will be approximately 1/2 of that ultimate strength. Now for aluminum, since we don't have that knee or elbow, we define the endurance limit at 10 to the power 8 cycles. So in aluminum, we define the endurance limit. So sigma E in aluminum is at 10 to the power 8 cycles. I don't want to go to too many details about fatigue. I teach in another graduate class the whole concept of fatigue. But this is all what we need to do, and Mr. Jae-Dong-San is going to break for us in fatigue 2 samples, one of aluminum and one of steel, under the same stress, and if everything is right, you're going to see that under the same stress, steel have a higher number of cycles to failure than aluminum. This is all what I wanted to give with that videotape. Thank you.